Welcome to this section of the course. We will be finding areas under the curves and integrate parametric equations. This section is going to be particularly long with 7 examples, so feel free to take a breather and pause the video anytime you wish. Right, in this first example, we've been asked to find the area under the curve with the equation of 9 over the square root of 4 plus 3x. Between x values being 0 and 4. Okay, so we are going to solve a problem where the upper and lower limit of x are 0 to 4 and the integral is 9 root 4 plus 3x with respect to x. How can we solve this? Well, from my experience, I would use u substitution here. Now, there is no right and wrong answer. You can use the u to be 4 plus 3x with the square root or without the square root. I'm going to leave it as without the square root. Therefore, when I differentiate du with respect to dx, I'm going to simply get 3. I need to isolate dx alone. So dx will be du over 3. Now, that means that I will have to change the limits of my integral to u as well. So some students find it helpful to use a tabular method for presentation. So I'm going to show that to you. X is going to be either 0 or 4, and u is going to be 3x plus 4. So when x is 0, we will have a 4 for u, and when x is 4, we will have 16. Therefore, this integral can be written as 4 to 16 as the limits on the integral. We will have a power of a half. So rather than writing it in the numerator, I'm going to write it with a negative power of a half here. And we are replacing dx here, this dx definition, with this dx definition. So we will have du over 3. But I'm going to bring the 3 here and put it under the 9, because that will simplify 9. I can simply put a 3 outside the bracket, because 9 over 3 is 3. And when I integrate u, I'm going to add 1 to this power. Minus 1 plus 1 is going to give me power of positive half. Dividing by half means multiplying by 2. And the limits are going to be 4 and 16. Now I can substitute the limits into the integral, into the definition or of the integral, which is already integrated. So I will use 3 outside the bracket. Actually, let me multiply 2 by 3 and write a 6 outside the bracket. Inside the bracket, I will have a square root of 16, take away square root of 4. Now that means that 6 will multiply by 4, take away 2, which is simply 12. The units are not clear here, so it could have been centimeter square or meter square. We're going to leave it as it is. Okay, so let's look at the next example. In example, we have two functions. F of x is sine of 2x and g of x is sine of x multiplied by cos of square x. Both of these end from 0 to pi over 2, but the area is bounded by two curves. This is where you have to subtract g of x from f of x. Now you can, because g of x is the lower curve and the high curve is f of x, you start with the high curve and you subtract the lower curve because we are going to subtract this region that I'm shading in red. That's the region that is taken out or cut out, therefore we need to subtract that area. So we can write this definition of f of x and g of x. In this case, the functions actually don't interact with each other. Sine of 2x is not related to sine x cos square of x. Therefore, we have to keep them as they are. Therefore, I'm just going to put it there and integrate it on the next slide. We can think about our trigonometric understanding. If we differentiate cos, what will we get? Differentiating cos of 2 theta 2x is going to give us negative sine, but we are missing and so let me put it here. Cos of 2x differentiated will give us negative sine, but with a factor of 2 at the front. Negative sine of 2x with a factor of 2. What's missing in our integral is a factor of minus 2. So we have to divide our answer by a factor of minus 2. When we put cos 2x there, we will have to divide by negative 2. So let's put that there. Then we are going to look at a function that would, when differentiated, would end up with cos square and sin x. If you add 1 up to the power of cos square, we'll get cos cube. So let's differentiate cos cube. If we differentiate cos cube of x, we will have cos square of x multiplied by 3, and the negative sign is there because the derivative of inside function cos itself is negative sign, just like the other example we did on the left hand side. So what's missing in our integral is actually a factor of 3. We already have a negative sign there, which is great. So we will need to simply just put a positive cos cube there, but with a factor of a third in front of it. Okay, so let me. So that's great. By the way, if you're stuck and you quite don't know why did I have a guess at this to be cos cube and started differentiating cos cube out of nowhere, there is also u substitution method that you can use. Okay, so the u substitution method would be simply calling u to be cos of x. Therefore, du by dx would have been sine of x. Sine of x. Now, we want to have dx alone, so we would have du over negative sine of x by dx there, and this would be our definition of dx. Now, come in here and simply just integral into two integrals and having sine of x there. Instead of cos square, we can write u square here, and instead of dx, we are going to have du here, but du is over negative sine of x. Now, this negative sign is also in front of the integral, so I can put it there, and actually, because it's already there, we will have a plus, because negative and negative will cancel each other, make a positive there. Now this sign will cancel away with that sine x, therefore we'll be left with integral of u square. Integral of u square is nothing but a third of u cubed. Now there are limits here that we will substitute there later. So the meaning of u, the definition of u was cos x, so therefore the answer here is a third of cos cube x, and that's exactly where that came from. Okay, so now let's substitute the limits into that integral and uh, evaluate the final answer. We will have a third of cos to the power of 3. When we substitute pi over 2, cos of pi over 2 is 0, and we will subtract, actually let's write minus half cos of also 2 times pi over 2 is simply just the pi. Cos is negative 1 at pi. Okay. So this half will multiply by negative 1 here. Instead was just for that. Now we will subtract when we substitute 0 into in this. So again, 1/3 of cos of 0. Cos of 0 will be 1, and we have a negative half. Cos of 0 again. 2 times 0 is 0, so this would be a half 1 as well. So we have 1/3 take away a half, which is negative 6, negative is 1/6, and negative 1/6 will make this a positive 1/6. And here we have simply a positive 1. So we actually positive times negative 1 times the negative half will give us positive half. So positive half plus a sixth will be 6 plus 2 over 12, which is 8 over 12, which is 2/3. Okay, so let's look at the next example. It's important that we write here square units. Right, in example 4, we are asked to integrate a parametric equation. We've been told to find area under the y curve with respect to x, but everything is in terms of t. What do? We don't know what is this dx. What can we do about this? Well, when you have any parametric equation, you can replace dx and you can differentiate. Don't forget, you can differentiate this x with respect to t, but you end up with dx over dt. Okay, so once we've done that, we can turn this integral from x and y into t, take it to the t work. What that means is that we can write y times by dx over dt, and because we will use this definition of y will be just in terms of t, and dx dt is in terms of t, and we can integrate with respect to t. This t and this t, dt and dt, algebraically will cancel out, and what we are doing is exactly what we were asked to do, integrating definition of y with respect to x. So let's look at this in more detail. I'm going to basically find what is dx by dt. So differentiating 5t squared will give us 10t. What we are going to substitute into the integral is t cubed multiplied by dx by dt, which is 10t, and we differentiate this with respect to t. because that's what the answer will be. So we can factorize the 10 out of the integral. This t with that t will give us t to the power of 4, and t to the power of 4 integrated will be 1/5 of t to the power of 5. Now that 10 over 5 will give us 2t to the power of 5. We don't have any limits in this integral, so we put the plus c. That's it. As easy as this. So don't forget this equation. Every time you see dy with respect to dx and you have parametric equations, you turn this into multiplied by dx dt, everything with respect to t dt. Okay, so put this in our toolbox and we'll use this again in our next example. This is continuation of the same example we were working on. Only this time we've been told that the limits of t are 2 and 1. Therefore, what we have to do is just substitute 2 and 1 for t once we've integrated. So going through the working out again, we went through this. So now we substitute 2 and 1 for the upper and lower bounds, and what we will get is this 2 to the power of 5 times by 2, take away 1 to the power of 5. Final answer will be 62. Okay, so let's look at the next example. This example, we are given a sketch of 0 to 9. These are in terms of x. So the question is telling us this is the x-axis, not t, and this is the y-axis. We have to find this area under the red curve, but we have x being in terms of t. So we don't know what the limits of the integral are. Yes, we know that we're going to use this equation and substitute values here, but we have some more work to do, because when x is 0 and when x is 9, we need to know what the value of t is. So let's find out what the value of t is. We are going to write t squared equals to 0, and there is only one value that it could be. T could be 0. Then t squared is 9, could be plus or minus 3. But we've been told that t is a positive value, so t can only be 0 and 3, positive 3. So our integral is going to go from 0 to 3. We are going to put the definition of y as it is under the integral, multiply that by dx. What is dx by dt? Dx by dt is 2t, write this there, 2t, and we're going to integrate this integral with respect to t now. Multiplying out the factors, we will have a factor of 4. Let's pull that outside the integral. T times t is t squared, and I'm just gonna write these so I don't make any errors. One more time. T times 3 is 3t squared. T squared times 3 is 3 squared, and I'll have negative 3 cubed, t cubed. So now integrating that with respect to t, we will keep the 4 there. T to the power of 2 will become t to the power of 3, and this 3 divided by 3 will cancel away. T to the power of 3 will become power of 4, and the negative remains here, and I'm going to write the factor of the quarter at the front. Multiplying the quarter into the integral, 4t cubed minus t to the power of 4. Now we said we are going to substitute 0 and 3 for values of t. Therefore, we will have 4 multiplied by 3 cubed, take away 3 to the power of 4, and subtracting 0 doesn't change anything. So we have 4 lots of 27 by 81. The final answer comes out to be 27. 27 square units. Okay, let's look at the next example. Example, we've been asked to find the area that is bounded by the loop. By loop, they mean where x value is going from 0 to 8. I've tried to shade in that region in red so it's clear. So, we've been told the limits of x value. Once again, we don't know what the limits of t is. And we know that when we integrate the parametric equation, we will have everything in terms of t. So once again, we are going to make use of this equation up there without putting the red box. So first, let's figure out what the values of t at the boundaries are. So when x is 0, 2t squared can only be 0. 0 by 2 is 0 and t will be 0. Now when x is 8, what's the value of t? Dividing everything by 2, we will have 4, and t could be positive or negative 2. Which value will we get? Okay, so x is positive. We are going to take the positive value for t. Alright, what this integral turns out to be? The definition of y remains as it is. So let me write that there. We are going to multiply by dx by dt. So dx by dt is simply 40, and we're going to integrate that with respect to t. So let's pull out the factor of 2 in front of the integral. We'll have t here, t squared actually, multiplied by 4 minus t squared. So integral remains as it is. 4t squared take away t to the power of 4 dt. Now using the power rule, let's leave the 4 where it is. Power of 3, 4 will be over 3, and this t will be power of 5 with a factor of a fifth to the front. Now the limits of t are going to be from 0 to 2. So we're going to substitute 2 into this equation. Let's write 16 over 3 first. 2 to the power of 3 is simply 8. And then we'll have 2 to the power of 5, which is 32. We will have 4 times 32 over 5. And when we substitute 0, we will subtract 0, so that doesn't change the equation. So what's the final answer? Okay, the answer is 17 and 1/15th, but there's one important fact that I forgot to mention. What we did was we found the area only in half of this section. Actually, the fact that I shaded these areas separately is that once we integrate using positive value of t, we are finding this area on top of the curve, on top in the top half of the shape, right? And because the fact that it's symmetrical, the value of t being negative 2 will give us the lower half of the shape. Therefore, all we have to do is say 17 1/15 will need to be multiplied by 2. Okay, so that's how you answer these questions. Right. See you in the next video.